Alright, so now we're going to take a little bit different perspective, something that's a little bit more general. So it accounts for a few more molecules that can affect pH and classify them as acids, which means they're lowering the pH, or bases, which means they're raising the pH. So that's what we're doing here. And it's a little bit more general, but it still fits into kind of what we've been talking about. And so nothing too wild here either. And so an acid is going to be something that donates protons. So it's a proton, which, what is a proton, by the way? Well, it's an H plus ion, right? It just has a proton, no electrons, no neutrons, typically. So it's a proton donor. So what does that make a base? What's the opposite? It's the opposite of donating. Well, the polite term, I guess, would be accepting. It's not taking them, it's accepting them. So bases are going to receive protons. It's like send and receive. Alright, so if we have a reaction like HCl plus NaOH, we get water and a salt. I think we've seen this exact reaction before a few times. And so this is our compound that's going to donate our H+, and this accepts the H+, because it's going to go on to that hydroxide. So this is our base, this is our acid. So everything we've talked about before lands in this definition. What it does is it unlocks some new stuff. So for example, ammonia. This is a weak base because it doesn't do this with 100% of the ammonias, but an H plus can be accepted by that lone pair, and we get ammonium. Alright. And so that's why ammonia is a weak base. Because this is like, 1% of ammonia that does this or something. Not 100%. Alright, another detail we can add is that there are compounds that can act as an acid or a base, just depending on the situation. So, they're a little bit versatile. So they can send out H pluses or they can receive H pluses. An example of this would be bicarbonate. So anything with the bicarbonate ion. So for example, sodium bicarbonate, NaHCO3, because bicarbonate is the HCO3 minus anion. Well, if we combine this with an acid, then we get H2CO3 and NaCl. And so this accepts a proton in this reaction. But if we combine this with a strong base, then it's going to send out, it's going to donate a proton. So that H goes bye-bye. And so this is a base up here, and this is it acting as an acid. And it's the same compound, it just depends. So if I have this guy here acting as a strong base, this one's going to act as an acid to compensate. And so you can use something like sodium bicarbonate, which is baking soda, by the way, to clean up acid spills, because it's a really easy way to neutralize it. Because what happens is then this, so if you've ever seen baking soda in an acid like vinegar or something like that, you might remember that there's a gas that's produced. Well, this guy is actually going to turn into a water and CO2. And so this gas that you see, those bubbles forming, that's CO2 because the H2CO3 undergoes a decomposition reaction. So there's actually 2 stages to making that CO2. Whereas over here, you're just locked in. It's just one step. If you ever do pool chemistry, your total alkalinity has to do with how much bicarbonate is floating around in your pool. And it will, because it can act as an acid or a base, that's really key to buffering. And so having a nice amount of total alkalinity actually helps your pool resist big swings in pH. So all these topics are related in all sorts of fields. So, in addition to pools, I'll also add that this is the key to our buffer system in our bloodstream. Remember how I talked about it being a tightly controlled pH? The fact that this can accept or donate protons helps level out those changes. But we'll get into more detail on that later. The other big thing is that water can also be an acid or a base. Alright, so it will also do this at the same time and self-ionize. And so if we have 2 waters, we can get them to react with each other and give us an H3O plus and an OH minus. And so this is why pure water has a pH, because it has the ability to generate H pluses or H3O pluses. So the one detail I'll add to that is this doesn't happen with all water, thankfully. It would be a mess dealing with water if it did. This is going to happen with very few water molecules. Very, very few, like less than 1 in a billion. The concentration of H3O plus in pure water is 10 to the minus 7 molar. So very, 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 very low. Very low. So generally, when you dissolve ions in a compound in water, it can conduct electricity. But this concentration is so low that pure water, by itself, even though it will self-ionize, doesn't generate enough ions to conduct electricity. So it's insulating. And that's kind of the key detail as well. So there's just a lot of pieces I'm laying out this week that we're going to build on next week. But the key idea here is we've got a little bit more general of a definition. And so that allows us to talk about these substances that can be an acid or a base, something like sodium bicarbonate. It's not the only example of this. You know, water can do it too. So water can become OH minus or H3O plus, so it can pick up and dump protons as well. It just depends on what it's reacting with. Alright, and so, you know, we've kind of introduced this stuff. Now we're going to step into a very specific experimental technique called titrations, and that's going to be probably definitely the longest video, because I'm just going to do it all in one shot this week. And like I said, I'm throwing it all out there this week because you have the titration lab, so it should help you out a lot with that. But it will build on these basic definitions that we've done so far, or well, basic and acidic definitions we've done so far. Alright.